All right, we got one more of these shear moments to do, so let's have a look. It's this one here. So what we got a triangular load on the beam. Now this gets a little trickier because really what you're doing graphical integration as you work your way from load to shear to moment. It's graphical integration. So what happens is each step of the way you add a power to the exponent on the function, basically. So if this is a linear function, basically x to the 0, this function will become x to the 1. That straight line there is x to the 1. And this becomes parabolic. That's x squared right in there. That's kind of how that works because you're doing graphical integration. So this is going to get a little tricky here because now we're already at x to the 1 with a load. So this will be a parabola based on x squared. And that means we're actually going to get into a cubic here. So it gets a little bit trickier, because we start with a triangular load. But the basics of it are the same. You want to start with the area of the triangular load. So that will be 1/2 times the height, which is -36. Remember on these load diagrams, keep your eye not so much on the which side of the diagram they're on as much as the direction of the arrows. So the arrows are pointing down, that means that's negative. So negative times 1, or excuse me, negative 36 times 1/2, because it's a triangle, and times the base of 9. So that's negative 162. All right, so once you have that, you can then get the shear diagram. I also showed the reactions there, which you would have to find, of course. So we have the reactions, and then all right, so we go from 0 up to 81. Okay, for the first 3 feet, there's no change. So after going from 0 up to that reaction on the left of 81, you have no change for the first 3 feet. And then you're going to have a change of negative 162 over the next 9 feet. So where you end up at is negative 81 after 9 feet. Then there's no change for 6 more feet. Then you hit this reaction, and that pulls you back up to 0. So this is what's happening with the shear. Now what happens here is it gets a little bit tricky from here on in, because what we're going to want to do here is a couple of things. We're going to want to know the areas under these pieces of the diagram. Now the rectangles are easy enough, of course. You just got this one, the area would just be, what, 81? And that would be kips times 3 meters. So that's easy enough. That's, 243. I guess those aren't kips in meters. I got a problem there. That's kips in feet. There we go. Kip feet, okay? And this one here is, this area is negative 81 times 6 feet. So that's negative 486 kip feet. Okay? But what's going on in the middle there gets a little trickier, because a couple of things. One, we got to figure out where that 0 point is, because that's the change from a positive to a negative area, which is significant. And the other thing is we got to find the area. So that's two challenges there that we have to work through. And this can involve some calculations here, like things do sometimes when we're doing engineering. So let's have a look at what we will do with this. So this stuff gets a little bit detailed, you might say, so let's have a look. All right, now what's happening here is the change in the shear is equal to the area under the load diagram. That's the fundamental relationship. So what you want to do here, I think, is come up with an area under the load diagram as you work your way across. Okay, now the first thing we're going to look for on this Well, first thing we want to do is use that relationship between change in shear and area under the load diagram to get an equation for that line, that parabola right here that's going down, okay? So we're going to look at a basic equation under this loading diagram as we go across. So we want to find the equation there of the curved line on the shear diagram. And to get that, we're going to use the fact that the change in shear is equal to the area under the load diagram. All right, now we want the slope of that line, because that'll help us to figure out this equation. The slope is negative 36 because it goes from 0 to that 36 kip per foot, but those arrows are pointing down, so that's why it's negative 36 over 9. So the slope of that line is actually negative 4, which is the ratio going from 0 here up to this top point there. It's a straight line, and that point the second point I marked there on the right is at 36 up, or actually down because it's negative, and 9 over. So the slope of that line is negative 4. Now I'm going to come up now with a generic diagram of that thing as I work my way over from the left towards the right. Now I'm not going to use x down here, I'm going to use the base, I'm going to call it. X is generally defined over here. I don't want to use x to define that base because I'm going to have to put in a x minus 3 kind of thing, and that's going to get a little messy on just the basic calculations. So what I'm going to do is I'm just going to work my way over and call that b, okay, instead of x. I can do the plus or minus 3 thing later if I need to, okay? So if I go over a distance b on that triangle, the height of the triangle is the slope times the base, which would actually be negative 4b. So what that means is the area of that triangle as I work my way from that vertex on the left to the right is 1/2 times the height, negative 4b times the base of b, is negative 2b squared. That's the area under that triangle, or of that triangle, you might say. Now, if you look at what's going on here then with the shear diagram, we're starting up here at 81. Then the change in shear is equal to the area under the load diagram. And we got an expression for the area under the load diagram. It's negative 2b squared. Okay? So the curved line here, as we work our way down, starts at 81. And then the shear, which is equal to the area under the load diagram, changes by negative 2b squared. Okay? So now I've got the equation for that line. It's 81 minus 2b squared. Now the first thing that I'd like to find out with that equation then is where this thing zeroes out, because that's going to be the change from a positive area on the left to a negative area on the right. So I'm going to take that equation, 81 minus 2b squared, and set it equal to 0. I just kind of work through the algebra on that. All right. So 81 minus 2b squared is 0, so 81 is 2b squared, so b squared is 40.5. So b is 6.364. Now really I'd like to know what x is, and x then is 3 plus b, because b is 0 right there. X, which starts over here, will be 3 plus whatever b is. So x will be 9.364. Okay? So that's where that thing zeroes out. Y'all good with that? And the key thing here is that the value of, the change in shear is equal to the area under the load diagram. That's what's going on here. So I found that area as I work my way across the load diagram. It's minus 2b squared. From there I can get the equation of that curved parabolic section of the shear diagram. It's 81 minus 2b squared. Okay. So that's what's up. All right. So I found out that it zeroes out at 9.364. Now, if that's the case, I'm going to have to integrate this thing out to get the area. There's no other way that I know to do it. I don't know, there are some equations for what they call parabolic spandrels, but all the same, I think I'll just integrate the thing. Okay? Yeah, that's what they call them. They're kind of like triangles, but they're maybe, so the hypotenuse, they got a parabolic line. Not quite sure on those things. I don't know. They might get a little tricky because, there's a difference between just taking a piece out of a parabola versus where you have the slope is 0 there and a slope of almost infinity here. And we're not quite sure how they define exactly how that parabola fits into that graph, But there are equations for these things. But all the same, we'll integrate it. Okay. What's that? Oh. Yeah, do it this way. Yeah. Actually, they're pretty simple equations. I'd have to look. But we're going to integrate the thing. So let's integrate it. All right. So what we're going to do is we're going to cut up that piece of the parabola like you do when you integrate into little slivers, little DAs. So here's a typical DA. We're going to come over a distance of B, and then we're going to find the height of that thing. And the height of that thing is 81 minus 2b squared. The width of that little rectangle there, that little element, is just db. Okay? So the area of that rectangle is whatever b is. You take 81 minus 2b squared and multiply by db. That's the area of a rectangle there. Now we're going to start counting these things up when b is 0. And we're going to end counting them up when b is 6.364. So those are the limits. Okay? So I'm just going to integrate that thing out. So it's 81 minus 2b squared. I'm going to do the integral of that from 0 to 6.364. Okay? When I do the integral, it's 81b minus 2b cubed over 3. I'm going to evaluate that from 0 to 6.364. So 81 times b, I'll put in that top limit, 6.364 minus 2 times 6.364 cubed over 3. Then I'll put in the lower limit, which is 0, 81 times 0 times minus 2 times 0 over 3.
Yeah. For those limits, on that 6.364, are you subtracting 3 from that 9 point?
Yeah.
364?
Yeah.
So starting over?
Yeah, because I'm basing this on b, not x.
Okay.
And that was my intent in doing this. I want to avoid the whole need to call it x minus 3.
Yeah.
And that turns into a mess on a number of things. And it's simpler just to independently define your base. Just call it b. It just works easier. Okay. So we good on doing the integration? Okay. Get the area, works out to be 343.7. I can find the second area if I like, which is the negative one on the right, area 2. Same equation, different limits. I'm going from 6.364 to 9, and that comes out to be negative 100.7. So now I've got the areas. Okay. The area of the first side is 343.7. That's on the left. To the right there, I've got a negative area of 100.7. So based on that, I can come up with the moment values. Okay. I'm going to start at 0. I'm going to go up in a linear fashion up to 243. That'll be a straight line. It's 3 feet over. Then for that first 6.364 feet of the triangular loading diagram, I increase by 343.7. That gets me up to 586.7. That's the maximum. That occurs right here where that graph flips from positive to negative. So the slope of the moment diagram is the value of the shear, which is 0 up there. That's the maximum. Then I'm going to drop by 100.7 to 486. So that's the curved section in there that represents the parabolic part of the shear diagram, right in there. Then I drop from there in a linear fashion at a straight line from 46 down to 0. Okay. So that's how I get from that from load to shear, and then from shear to the moment diagram. Y'all doing all right with that? Okay. So that's probably the most complicated of the bunch because you have to get it into some calculus there to work through that. All right. So let's see. I've got another one there on the following page, I think. And let's see if you can get the values in on that one. So I've got this load here. I've got a distributed load from A to B, point load at C, and a couple at D. And I want to work my way down through that from shear to moment. So why don't you see if you can get the values put in there. So where I would start with that is get the area under that loading diagram from A to B. Okay, so get the area under the rectangle from A to B. You know, I'd always start with that. You got the reactions too. So the area under the rectangle, that's going to be the change in shear. That's going to drop the shear diagram by 4 is what that's going to do over that 2-meter span. You'll get into the shear diagram, okay? So it's a straight slope down where that distributed load is. -2. So 0 up to 12 on account of the reaction, drops by 4 down to 8. No change until you hit C, then an immediate drop at 12 down to -4. Then no change until you hit the reaction and back up. Is that all right? And that couple has no direct influence on the shear diagram, other than the reactions, which is really the influence it has. The fact that that couple's there doesn't make any changes in the shear diagram. Okay. So, we all right with that? Then the next thing you'd want to do here would be to break this up into pieces and start finding the areas of the pieces. I would probably find an intermediate area. You know, you're going to have 2 meters and then 2 meters. Find the area on either side of that. The reason is you got that couple there that's going to throw a jump into the moment diagram. So you're going to want to know the area on the other side of that, so you can kind of see what the value of moment is right when that jump's going to happen. Okay. Okay. So you want to be finding the areas next. Is what you'd want to do. And then once you've got those areas represent changes in the moment diagram. So you see the rules from going from load to shear are very similar to the rules that go from shear to moment. They're the same sort of things. The area of the previous diagram gets you the change in the next. The value of the previous diagram gets you the slope on the next. Okay? And what these are, they're graphical integrations is what they are. Okay? So we're doing all right with that? Working through. And whenever I see those areas, I just go ahead and calculate them, you know. That's what I want to do. Yeah, they kind of depend on the values. You've got rectangles and a trapezoid there, I think.
Oh, okay, that's what's happening here. I was trying to.
Right, yeah, that's it. See, you've got a pair for that gauge on that value right there, so you want to get the area on either side of it where the jump's going to happen.
Okay.
All right. So once we've got those, then we can go ahead and plot up a moment diagram based on those values. Okay. So again, the areas under the shear diagram are the changes in moment is what they are. So these diagrams always start and end at 0. And these are changes, so that'd be 20, 36, drops by 8 to 28. Okay, now the couple there, if you look at the couple, it's 20. It's counterclockwise 20. Now you got to remember to change the sign on that, so that's going to drop by 20 down to 8. And that last change will get you back down to 0. That's the sequencing on that, okay?
How'd you get that 36?
36 is 20 plus 16. So I get the 20 I've got plus the area of the next piece there, which is 16. Okay. And then 36 minus 8 is 28. Then I drop by 20, so I'm at 28 minus 20 equals 8. And then 8 minus 0, or excuse me, 8 minus 8 is equal to 0. So that's the calculations there. You're just adding and subtracting the areas. You do have to remember to switch the sign on that couple. That'll cause an immediate jump down on the moment diagram. Okay.
I think it's this. Can you go back to that last one? I think I got my area wrong.
Which one?
-8.
What, -8? What you're doing, you got, that's -4 times just a 2 meter span.
No, 1 point.
Oh, up here, 16 or?
Yeah,
Yeah, it's just 8 by 2, height of 8, base of 2. Is that one? Yeah, 8 by 2. So, you doing all right? Okay, good. There we go. Right, so that's the basics of putting these together. All right, now, so what we've done here so far for beams is we found the centroid on the cross section, which is where the neutral axis is. We found the moment of inertia based on that centroidal location, and now we've got shear and moment diagrams. So now we got enough pieces to put together to design a beam. Okay, now the first thing that you look at to accomplish this is the bending stress. Okay. It's also called beam flexure because the beam flexes. Okay, so we're on page 830 is where we're at. Okay. Okay, here's a picture of a beam failure there. They have a glulam sort of beam. They're applying a load to it. This is kind of a pretty classic sort of jig there. What you do is you have your beam, you know, like that. You got a couple supports on the beam, and then you load it. Now, they don't like to load it straight at one point because they kind of get a stress concentration there. So what they want to do is load it in 2 points, and that gets kind of a smoother bend to it. So you're looking more at that classic kind of bending stress. So that's what's happening there, okay? To that beam, and what you're seeing there is the failure. The failure is happening in the middle of the beam where the bending is most extreme, and it's propagating from the lower level of the beam, kind of working its way up. So what's happening there on account of that load is that beam is failing in tension on the bottom, stretching out on the bottom, and it's not able to hold together. And once that first laminate breaks, the crack kind of propagates its way up through. So it's happening, okay? So that's a pretty classic normal stress failure there for a beam. They have this two-sided jig to spread the load is what they're doing, okay? So that's pretty common way to test these things. So what happens when you load a beam up is it flexes, of course, and you have that neutral axis running down the middle. That's found from the centroid of the top. And then what you have then, the neutral axis is in either tension or compression. Okay, so the beam has to hold that right angle shape. The sheets of atoms aren't free to slide like the sheets of the phone book are. there's atomic bonds that hold them together. So this side gets kind of pushed in. So this side's in compression, and the bottom side, to hold its shape, gets stretched. So it's in tension. Okay? Neutral axis is the axis that is in either tension or compression. All right, so let's have a look at this. What we have here, just to simplify the derivation a bit, we've got a cantilever, we've got a load on the end, kind of like a diving board, and we're going to pull out a little piece of it here, this DS piece. Now there's a curvature radius on this that we'll call rho. Rho is kind of like R, the radius, but it's for a non-circular curve. Rho is a more general term. I guess it could be for a circular curve too, but rho will work for non-circular curves also. So what we got in there is a little piece of a change in angle there, right there. Call that d theta. We've got ds, which is along the arc of the curve, which is very, very close to dx, which is in a straight line. For our engineering materials, we don't have a huge amount of deformation there. Okay. So the bigger rho is, the less extreme the curvature. So the smaller rho is, the more extreme the curvature. So kappa, which is called the degree of curvature, is 1 over rho, 1 over the radius. dx and ds are approximately the same. So if we want to analyze that, we can pull that little piece of the beam out, okay? And what we'll have then will be a little piece of beam. Okay, so there's our d theta. Here's our little piece of beam. We've got the neutral axis running down the middle. And let's draw it before we start bending this thing. So let's say when it's just a nice clean piece of beam that's a rectangle, we're going to put 2 lines on it, both of equal length. One will be at the neutral axis. The other will be a distance below the neutral axis that we'll call y. Okay. Then we're going to bend that beam, and we're going to look at what happens to those 2 lines we drew. They're going to see what's going to happen, being as the first line's on the neutral axis, it doesn't change length, but the one below will. Okay, so here we're looking at those 2 lines. There they are, but the one below gets shorter because it's getting curved in. Okay, and we're going to look at how much shorter it gets. So you all good with that?
So the first line is the neutral axis.
Right, yeah, and it won't change length, but the one below will. Okay. All right, now we're going to approximate, this is really a sector of some sort of curved surface, a circle, probably not a circle, but something like that. We're going to approximate that as a triangle. So we're going to go in from that ds to a dx, okay? So there's our dx, and there's ds, okay? So we're going to approximate ds as dx, and we're going to have a triangle there. Okay. So what we're going to look at then is the strain that happens in that lower line. We're going to call that epsilon x, okay? So what epsilon x is the change in length over the original length, which is the L prime, the new length, minus the original length L over L, okay? Now delta L over L proportionally is the same thing as delta rho over rho, okay? So these are similar triangles. We got the red one there, we got the green one, they're similar. So we can say that delta L is to L is delta rho is to rho, okay? On account of those being similar triangles. And that'll be minus y over rho. Delta rho is minus y, is what that is, because y is getting shorter, okay? So based on that, we can say that the strain, which is delta L over L, is equal to negative y over rho. Now 1 over rho is kappa, so the strain is kappa times whatever that y distance is. The stress, if we're within the proportional limit, we can multiply the strain by E. Okay? So, and what the strain is kappa y. So here's a nice little expression for the stress. Now basically all that's telling us here so far that we can really use is the further you are from the neutral axis, the bigger the strain and the bigger the stress. That's basically what that means. It's proportional. Okay? That's why that beam started to fail on the bottom, because the stress is biggest at the bottom, because the curving and deformation is more extreme there. So you get more deformation, more strain, more stress. It's a linear relationship. Okay. So sigma x, the stress, is proportional to how far from the neutral axis you are. So if it's a linear relationship, which it is, sigma x over y is constant. Okay? So that's what we get out of that little bit. The further you get from the neutral axis, the more strain and stress you've got, and it's a linear relationship. That's basically what we've got there. Now let's look a little bit at the relationship there between moment and stress. So we'll have a look at 831 now. Now here's the moment off the moment diagram. That's kind of that couple that builds up internally in the beam. Yeah, we found that when we did the equations. The diagrams reflect the equations. Now let's have a look at what that is. If you've got a beam that's flexing down, you've got this neutral axis here. Above that, you're going to have compression pushing in on the beam, and below it, you're going to have tension pulling on the beam. As you get further and further away from the neutral axis, those stresses get bigger and bigger, and I'm showing that by the length of the vectors there, the length of the arrows. Now, if you kind of put a resultant in here for all of these, you're going to get something like that on the bottom and something like that on the top, okay? They're pushing opposite directions, and what you get there from the tensile stress on the bottom and the compressive stress on the top is basically a couple, and the magnitude of that couple is what the moment is off the moment equation, okay? And off the moment diagram. So that pulling on the bottom and pushing on the top create a couple, all right? Now, to find the magnitude of all this, what you would look at here would be the cross-section of the beam. You know, there's your neutral axis. You take a little dA thing there, you're going to have a stress on that. This is going to be getting pushed on here. And there might be a little dA down there that's getting pulled on. That's kind of what's going on there. So to figure out how much of a couple that's creating, we want to find the force. That would be the stress times the area over which it acts, sigma x dA. Okay. Then what we want to do would be to add a moment arm, which would be how far from the neutral axis you are, and that's y. So y times sigma x dA is the moment. And when you add up all the possible dAs in there with the integral sign, you'll get that moment. So that's the basic fundamental relationship between the stress in the beam and the moment off the moment diagram. Bigger the moment, the more bending, the bigger the stress. Okay. All right. Now to actually do something with this, because we don't want to be running integrals all the time when we're working, you know, we want a simpler equation. We're going to do a little mathematical trick here. We're going to put in a term of y over y into that expression. Y over y just equals 1, so I could put that in there. But what that allows me to do is to find this sigma x over y, which is a constant. Okay, we established that earlier. If it's a constant, it can come outside the integral sign. So what's left behind in the integral sign is y squared dA, which is the integral of y squared dA, of course, and that is the moment of inertia by definition. So what you get is this basic relationship that the moment is equal to the stress times I, the moment of inertia, divided by y, how far you are from the neutral axis. Okay. Now what we're interested in doing here, see, normally we draw that moment diagram first, so we know what the moment is. We want to find the stress. So we can rearrange that equation to solve it for the stress. It's my over I. To get the maximum stress, we want to maximize y. Okay, and that is on the edge of the beam, because that's as far from the neutral axis as you can get, and that is where the bending is most extreme and the strain and the stress are most extreme. So we call that C, is what we call it, which is y max. So this would be C on the top, say, and C on the bottom, and they're both equal to y max. So I guess you'd have to define which side you're on. If you've got a symmetrical beam, they're the same, but if you got something that isn't symmetrical, they're not, okay? So we have to be a little careful how we define that. But anyway, the bottom line is right there. The maximum stress is the moment off the moment diagram times C, which is the distance from the neutral axis to the edge of the beam where that stress and strain are greatest, divided by the moment of inertia. Okay. And sometimes they combine C and I together because they're constant for a given beam cross-section and call it what they call the section modulus, and just say sigma max is M over S. Though normally I see it in this equation in the form you see on the top. Sigma max is MC over I. And that is, it's in the upper right-hand corner of the back of the formula sheet. I don't have a number on it, but that's what it is. Okay? So that's a pretty fundamental equation. You see that an awful lot when you're designing structures. It relates the moment and bending in a beam and the beam section shape properties to the stress. Is what it does. Okay. Now the other last little thing here is we developed earlier that the stress is minus E kappa times Y. We can plug that into that general moment equation and get a different expression for M. It's minus E kappa I. We can back solve that for kappa, and that's minus M over EI. Well, that'll come in handy later when we're doing deflections, okay? But for now, we'll be using this equation right there. Sigma is MC over I. Okay. So are we doing all right with that? Okay. How about, I'll give you one of these to do, but I'll make this due next week. This will be due Wednesday. That'll be the 11th, I think. Okay. So we'll put that out there. Now check and see if you got a 344. It ought to be a beam, simply supported beam that looks a little bit like that one we just did. It would be on its own page, I think. Anybody got a 344?
Oh, that's
You got it? What is it at? Is there a page number?
25 feet.
25D. You may not have 25D, so if you don't have it, I've got a photocopy. You know. Yeah, you may not have 25D. You got it? No. All right, so this is on page 25D. I've got it in Moodle also. So if you're online, have a look. If you've got a newer packet, you've got it. If you have an older packet, you don't, and you can get it out of Moodle if you don't have it in your packet. Okay. And that'll be due next week. We'll get to that later. Okay. So we're good. Okay.